Simon Says subscribe and click on the bell icon to receive notifications.
Welcome. Thank you for choosing our MySQL Database Administration and Development course. We hope you enjoy it. In this course, we're going to talk about the internal architecture of the MySQL Database Management System, which going forward, we're going to simply refer to as MySQL. In addition to looking at the internal architecture of MySQL, we're also going to look at the basic principles, the fundamental foundational principles that make a database management system what it is. And once we've laid that foundational groundwork, we're going to look at how to design a database and then develop it within the MySQL environment. Then, having a database, we're going to discuss how to keep it secure, how to secure the server, and how to secure the data. And then the routine maintenance that accompanies administering any kind of database system, from backing up the data to performance enhancements to monitoring and so on. Once we've covered these foundational principles of administration of the database system, we're going to look at a couple advanced topics. Data replication, that is moving data in near real time from one server to another server, and high availability, ensuring that our database, the database that we're responsible for as DBAs, that database will always be available for the business. So this begs the question, why study MySQL or any other database management system for that matter? Well, because databases and data in general, but the database specifically, is generally the center of any business. Whether it's an online business, a brick and mortars business, a nonprofit, government agency, data is at the center of that organization. It is the lifeblood of the business. And MySQL is the most popular open source database management system currently in use. And not only that, but MySQL is number 3 overall in the database market, with Oracle and Microsoft's SQL Server holding the number 1 and number 2 spots, respectively. Also, MySQL is part of the LAMP stack: Linux, Apache, MySQL, and PHP. MySQL is part of the LAMP stack, a very popular collection of technologies that some estimate currently support some 80% of websites on the internet. So what is a database? Well, a database is simply a container of data, of information. And we'll use those two words interchangeably, but technically, data is not information. So a database is a container of data, of information that's organized in some way so that we can retrieve that data quickly. Now, a database can be as simple as a well-organized stack of index cards, or a notebook with information that's well organized on different pages of the notebook so that we can find it quickly. But a database management system hides from us all of the complexity, all of the plumbing that's necessary for the storage of the data and the mechanisms that are used to find and retrieve and return that data to us. And through this level of abstraction, we're able to store just about any kind of data that we're interested in putting into the database system, and then finding that data, retrieving it, and using it within our applications however we see fit. That's the database management system. So the database management system, MySQL, contains databases. The databases contain tables. The tables contain columns. The columns contain the data. When we take a collection of columns, a tuple of columns, that represents a row in the table. One row in the table is an instance of some related data. Well, database management systems have fundamental principles that define them, and ACID is one of those fundamental principles that define a database system. The acronym refers to atomicity, consistency, isolation, and durability. When we talk about doing something to the database, whether that's inserting data, changing data, a combination of the two, deleting data, a combination of any actions that we want to occur on the database, an ACID compliant database must perform our collection of actions as a single unit. And if it is unable to execute our collection of actions as a single unit, it must undo any part of that collection of actions to put the database back into the state it was in prior to attempting to execute that collection of actions. So the atomicity of actions means if given some collection of actions to take against the database, they either need to all occur successfully or none of them occur. Consistency refers to the database protecting itself from actions that may corrupt the data. Isolation refers to the ability to have multiple users working within the database simultaneously without impacting each other or the data that each of the users is working with. Durability protects the data from system failures, so that if we make changes to the database and the server, for whatever reason, fails, those changes that we believe were successfully completed on the database are recorded somewhere so that the database will be in a consistent state with our changes recorded, even in the face of complete failure of the system. So how is it that MySQL implements these ACID principles? Well, we haven't gotten there yet. However, of the multiple storage engines that are available for use within the MySQL system, only one, InnoDB, is ACID compliant. So keep that in mind as we move forward. Within the MySQL database running the InnoDB storage engine, we get transactional support either implicitly or explicitly by using transactional control statements within our SQL code. All transactional statements are written to the log and then to disk. The consistency principle is supported by the binary log and the locking system within the database. Again, locks ensure data integrity by isolating the transactions. So we have support for the isolation principle. And the durability principle is again supported by the binary log file that records all actions against the database. MySQL is unique in that it allows the use of different storage engines to support different types of applications for the database. In fact, we can not only choose which storage engine to use, we can mix the storage engines within a single application, which allows an enormous amount of customization for the application. MySQL runs on all of the popular operating systems, Linux, Solaris, Windows, Mac, and so on. And again, one of the most powerful features of MySQL are the different storage engines that we can apply to our problem, to our application. And no matter which storage engine or mix of storage engines that we're using to support our application, the API, the interface that we use for managing the data within any of those storage engines is consistent. Again, this makes MySQL unique in the database world. To begin our examination of the MySQL architecture, we're going to take a bird's eye view, a very high-level view of the categories within which the different components of the architecture reside. And that first category contains the connection and authentication manager, as well as the thread manager. We're going to look at each of these components in much more detail. But again, to get an understanding of the high-level framework of the MySQL architecture, we're going to group these into categories for now. So the next step after getting a connection to the database server is to parse the query. And as we'll see, this is actually a fairly complex process. But in this case, logically, the next step is the parser components. Once the query is parsed, we have two possibilities. Either the query has already been seen by the MySQL database, in which case it's going to be stored in the cache, or the query is going to be passed to the optimizer so that a query tree, the path of access to the data, can be developed. Then one of the components within this optimizer category is going to execute that query against the storage engine. Recall that the MySQL architecture allows us to plug different storage engines into the database architecture, and we can mix those storage engines for our application. And as we'll see, there is a good selection of different types of storage engines which we can select from or combine to best serve our application. So with this high-level framework in mind, let's take a step down and look at each of the components within these categories. So in our manager category, where the connection and the authentication and the thread assignment occurs, there are actually many different components that perform those tasks. There is an authentication component. That component is responsible for ensuring the security of any attempted connection. This is where a user and their password is authenticated for connection to the MySQL database. And that connection can either be a local connection, so from the same machine, or it can be a remote connection over a network to the machine on which the MySQL database resides. And there are two components for dealing with those connections, either local client connection or remote client connections. Each are managed by those respective components. And once we have that connection, the dispatcher and scheduler is responsible for ensuring that the connection has a thread on which the work can be accomplished. So things that are important to note about this category of functionality provided by MySQL is that when we connect to the MySQL database, our connection gets a separate thread of execution. Now, this process has been greatly improved in the latest version of MySQL 5.6 to provide us a much more stable and reliable concurrent thread pool. When our connection is assigned a thread, we're also assigned resources for the query execution. And these resources are those that are needed for management of the query and the return data from the database. So the read buffer, the sort buffer, the temp table, these are resources that are dynamically assigned to our connection thread and can be administered by the DBA when necessary for optimizing the performance. And MySQL is very flexible in its connection protocols. Any program using a variety of different connection protocols, ODBC, JDBC, PHP connection, can utilize the services of the MySQL database. In addition, there are several administrative tools, either open source or fee-based, that can connect either locally or remotely to any MySQL database. That's important to note that the remote connections occur over TCP/IP, while the local connections can be accomplished over either TCP/IP, if you're in a Linux environment, the Unix sockets, shared memory, and if you're in Windows environment, pipes, NT pipes. So once we've gotten our connection and we've passed our query into the MySQL environment, we have a thread with dynamically allocated resources for execution of that query. The query is then passed to the parser. The parser category has several components that comprise this parse function within the MySQL architecture. The first step is to parse the query, and parsing the query is ensuring that the SQL statements are legal SQL statements, that the keywords are correct, that the arguments passed to the statement are in the order in which the SQL statement expects them, and so on. And then the authorization of that query, whether or not that query has the authority, has the permissions to access the resources that it needs to execute. And the query may be rewritten based on the outcome of the parsing function and the optimizer function. So the query optimizer is responsible for examining the statistics on the data within the database and all of the possible paths to access the data required by the query, finding the best path and building a, quote, query tree, unquote, to execute that query based on this developed best path. Then the query is passed to the plan executor. The plan executor is responsible, obviously, for executing the query plan, the query tree, as it was developed by the optimizer, returning the data then to the user. Then there's a utility component that executes data definition language statements and other utility statements within the MySQL environment. In summary, the parser performs both a lexical and a syntactic analysis of the query. The lexical analysis identifies the tokens and the other values or variables within the statement, and the syntactic analysis validates that the tokens and the values make sense, that is, that they are valid SQL statements. Then the query optimizer finds the best execution plan for the query. This can be problematic because the query optimizer will continue to search for a plan until it finds what it believes is the best plan. And the search is exhaustive. So at times, as administrators, we need to guide the query optimizer to limit this search in order to optimize performance. So the next level in our architectural framework is the selectable storage engines. Of the storage engines, they each have their own implementation of a lock manager. This is the component that's responsible for protecting the data to ensure the consistency of the data when multiple users are connected to the database. The buffer manager is responsible for moving data from the disk to the memories so that required data is in memory to respond to queries. The log manager is responsible for the durability of any changes to the database. So as we said, the MySQL storage engine is a pluggable component in the architecture. There are several different storage engines that can be used either individually or in combination to meet the requirements of our application. Two of the most common storage engines are the InnoDB and the MyISAM storage engines. But there are others. There's an in-memory storage engine, there's the NDB or cluster storage engine, there's the comma-separated values storage engines, and there's others on top of those. But again, the two most common, especially for transactional systems, the most common and only ACID compliant storage engine is the InnoDB engine. And the other common storage engine is the MyISAM. So in this course, we're going to focus on the InnoDB engine, and we will demonstrate how to mix the engines, especially the InnoDB and the memory storage engine, to optimize the performance of a MySQL installation, but we're not going to examine in detail any of the other storage engines. One of the other very important considerations when selecting a storage engine is not only the requirements of the application, but performance implications. Again, if the application is transactional and we're trying to adhere to the ACID principles, then we only have one choice, and that's the InnoDB storage engine. However, one of the other considerations is the locking granularity, which refers to when data is being accessed, whether or not during that access the row on which we're acting is locked, or whether the entire table is locked. This has a profound impact on the concurrency permitted within the database. So just as a summary, again, we're going to focus on the InnoDB, and we will demonstrate the combination of the InnoDB and the memory storage engines in an application. But our focus is going to be on transactional application support using the InnoDB storage engine. The final category that we want to examine is the utilities in the shared components category. This category has a lot of components that manage the MySQL environment, including the component that manages the replication of data. So putting this all together, we can see, in contrast to our high-level view of the MySQL architecture, that the MySQL database system is actually an amazingly complex system that's composed of, in this case, high-level components within these categories. And if we took another step down into this architecture, we'd see that even these components are made up of subcomponents, and so on. This is another characteristic of the MySQL database management system that makes it unique. And notice that the query optimizer is highlighted in this diagram, because much of the other functionality provided by MySQL, and in fact other database management systems like SQL Server or Oracle, are fairly standard. Authentication of users is a fairly standard function within any database system, in fact, any application system. The parsing, the lexical and syntactic analysis of queries, a fairly standard function. However, the gold, the most important part of any database system is its brains in how it can find the best path to the data. That's the function of the query optimizer. How can I use the statistical information within the database to determine the best, fastest path to the data that I need? That's the function of the query optimizer. And every database system, whether MySQL, SQL Server, Postgres, Oracle, and DB2, and so on, this is where the rubber meets the road in the query optimizer. So as a summary, the MySQL architecture is unique in that it offers this pluggable storage engine architecture where we can combine different storage engines, assigning specific data to a storage engine to meet the needs of our application. And that no matter which storage engine we select to support our application, the interface for using that storage engine is consistent across all of the storage engines. And the MySQL database management system, beyond the uniqueness provided by the pluggable storage engine architecture, provides an amazingly robust implementation because of its modularity. So where can we install MySQL? Well, again, MySQL is available for Windows, it's available for Macintosh, it's available for Linux, Solaris, and so on. Now we're going to demonstrate the installation of MySQL on Windows and Linux. However, going forward, after we demonstrate the installation, going forward, all of our demonstrations will be on the Linux platform. The reason for this is that the Linux platform is the preferred platform in the real world for the implementation of the MySQL database. So we want to be in that realm for the rest of our demonstrations. When we demonstrate the installation, we're going to see that we have options for the version of MySQL that we want to install. The MySQL community maintains older releases for download. However, we're going to select the most recent stable release. And furthermore, we are not going to download and build source releases. We're going to download and install the binary release for the targeted operating systems. So let's go look at this installation process. The first step in installing the MySQL database system is to download the necessary files from the MySQL.com website. We have a lot of selections here. However, what we're going to focus on is the community server. This is the freely available MySQL database management system. So we're going to click on this. There are multiple versions of the community server available, including archived versions. We're interested in the 5.6 version. You could install the 5.5. However, there are performance improvements in the 5.6 version that make it worthwhile to install. So if we go down to the available downloads, we're going to select the generic Linux bundle. And it's important to get the bundle because we're going to get not only the server, we're going to get the client tools, we're going to get testing tools, development tools, everything we need to create a MySQL database environment. Now, on our server, we are running Ubuntu 12.10. So there is no direct build for MySQL targeted at Ubuntu. So we're going to take the generic Linux implementation. And because I am running a 32-bit version of Ubuntu, we're going to take the 32-bit RPM bundle. When we click on the download button, you'll be asked to create an Oracle account in order to download the file. We've already done that and we are logged in as that user, so we can directly download this bundle. So we have the download now, and we're going to untar this file. Notice that within the tarball, we have multiple RPM packages. We have a server package, we have the client package, the test, the development, and so on. And the next step is to simplify the installation, is to convert the RPM into a Debian package. So we're going to do that with the Alien tool. And if you don't have this installed on your system, just do an apt-get. Use the advanced package tool and do an apt-get install Alien and get this installed. So we're going to convert the server RPM package and ensure that we also convert the scripts associated with that package to make the installation painless. So the conversion completed. Now we can do the installation using this command. And again, this will take a few minutes. So with the installation completed, it's now time to start the server with this command. and we can verify that the server is running, and there we have it. So the basic installation involved downloading the file in order to capture the necessary dependencies and simplify the installation process. We converted the downloaded RPM file into a Debian package. We install the Debian package and we start the server, and as we can see from the process listing, we have the MySQL database now running on our system. Now, with our installation complete, it's important to point out that there are other methods for the installation of the MySQL Server database system. Because this course is not focused on Linux administrative tasks, the process that was demonstrated was the simplest and most straightforward process for the installation. So now that we have our server installed and running, we need to immediately address some issues with the default installation. Unlike previous versions of the MySQL database system, version 5.6 does not create an empty password root user. In fact, it creates a root user with a randomly assigned password to increase the security of the initial installation. So we're going to have to go in and address those user security issues with our installation. Then we're going to have to test the installation to ensure that it is running properly. And then there are some default settings, such as the time zone tables, that need to be populated. If this is a production system, we'd want to make sure that the MySQL daemon, the service itself, is set for automatic start and stop with the operating system. So let's go look at some of that code to accomplish these tasks. After installing the server, the next step is to install the client tools. We're going to simply repeat the steps that we completed for the server installation, and this time we're going to do it for the client. We have an RPM package for the client tools, and we're going to convert that client RPM into a Debian package using the alien tool. Don't forget to include the scripts directive. Okay, so our package was converted, and we now have a Debian package for our client tools. And we're going to do the installation now the same as we did with the server, and this is going to provide us the tools we need to be able to communicate, to administer the server. Okay, so now we have our client tools installed, our server is running, we have verified that. However, if we try to connect to the server as root with a password, and we're going to connect to the MySQL database, it wants a password because in 5.6 they've locked the default installation down by assigning a random password to the root directory. In previous versions, the root directory had no password at all, which is obviously very dangerous to the security of the server. So where is this default password? So according to the documentation, MySQL, during the installation process, created a random password and put it into a file that it wrote to the root directory. So let's go look at the root directory. Notice that I am super user in this window, and there it is. .mysql_secret contains the random password assigned to the root account. So let's take a look at that file, and there it is. This is our randomly assigned root password, and we need to use that to log into the system. And there is nothing else we can do when connecting to the MySQL server for the first time other than change this password. Now, there's another approach to doing this. Let's try this, and if it doesn't work for you, then I'll show you the other. There, so we're in. So now if this doesn't work for you, for some reason doesn't work for you, before we forget, let's reset the password for our root user, because it is a requirement that on the first connection to the server after installation using the root user, we must change this password. There are a couple of approaches for changing the root user password. One is to go into the MySQL command prompt and use the command set password. So another approach is to use the MySQL admin tool, identify the user and the command that we want to execute, password. So this tells the MySQL admin tool that we want to change the password for this user. And now we must enter our current password and the new password and confirm the new password, and we're done. So now we have changed the default random password assigned to the root account during the installation process. Again, this is the second of the possible methods for changing the root password, and in fact any password. So here's another. From within the client command line tool, we're going to update the MySQL user table. We're going to set the password equal to password encrypted term, and you can see that 4 rows were affected. So we updated 4 rows in the user table that correspond to the user root and change the password for that user. If we use this process for updating the password, we now need to flush the privileges and restart the MySQL server. So this is a little more work than just using the admin tool, but it works. So 3 different ways of changing the password for the root account. This should be the very first thing you do after the installation is complete. So now let's test the installation and see the status of our server. Using the command show status, we can see all of the variable settings for our MySQL server. And we'll discuss most of these throughout the course, but this confirms for us that the server is running, it is configured, and we are connected to it. So one of the other commands is show databases. Don't forget your semicolon. And these are the databases that are currently installed on the server. So we have 4 databases installed. Let's switch to the test database. And we're going to ask to show the tables in test. There is nothing in the test database. So let's look at the MySQL database and show tables in MySQL. Don't forget your semicolon. And there we have a list of all of the tables in the MySQL database. So let's look inside one of these tables. Don't forget your semicolon. And this is the empty table for time zone. Okay, so let's fix the time zone issue. To do that, we're going to pick up the time zone information from the Ubuntu system. There is a zone info database in the user share folder, and we're going to pipe that to our MySQL as the root user. So asks for our password, then this tool loads the zone information into the time zone table. Now we'll notice that there was nothing in the time zone table in our last select from that table. Now we select from it, and there are 474 rows. So this is one of those initial configuration issues that has to be done manually to get our server ready for the production environment. If you followed along with the demonstration of the installation of MySQL, then you should have a working version of MySQL version 5.6 database server as well as the client tools. Now this isn't the only process for installation of the system, but it is the simplest and was chosen because it doesn't rely on any expertise with Linux administration. So a few simple scripts and the installation process was automated for us. And following the installation, we secured the server, although in 5.6, the root password is automatically randomized for us. In previous versions, the root password was blank and required that post-installation a password be assigned to the root user of the system. Also, following the installation, we configured the time zone table. As we move forward, we're going to see other configuration settings that we can manipulate to increase the performance of the installation. Now that we have our database server installed and running on our system, we're going to discuss database design. And we're going to do this now before we talk any more about administration of the server, because we need to have a database that we can exercise on the server to test the performance. Recall that a database is a container. It's a container of data. It organizes the data in such a way so that we can get that data fast when we need it for our application. That's its primary function. Store the data, keep it safe, and when we ask with a SQL statement, give us that data as fast as possible so that we can feed the application and indirectly service our customers. One of the reasons we use a database system instead of, say, a flat file is because we're able to organize the data in the database system into tables, and those tables get related with one another, and the organization of the data within the tables and the tables within the database and the relations between those tables, all of that has a profound impact on the performance of the database system. So we need to learn how to build an efficient database. And like most design professions, a database architect has a set of tools and a language that is used in the design process. The standard for database design is an entity relation diagram. An ER diagram is simply a graphical representation of the tables, the data within the tables, and any relationship between the data in the tables. And because it's this visual representation, it's easy to discuss with other DBAs, with other architects, with the application developers, because a picture speaks 1,000 words. When we look at the ER diagram, we're going to see that there are entities, and these entities are represented by a rectangle, and the rectangle has a name, and within that rectangle are listed the attributes of that entity. The entity may represent something physical, like a person or a product, but it may also represent something conceptual. The important thing to remember about an entity is that every entity must be uniquely identifiable. That is, that it must have a unique attribute or set of attributes to be used as a key to identify that entity. A relation is basic to ER diagramming, entity relation diagramming. The relation defines the connection between any two data elements. When we build our ER diagram, we're going to have relations, we're going to have entities, the entities are going to have relations with one another, the entities will have attributes which translate to the columns in the table. Each column, each attribute, must be uniquely named within the table. They don't mix data types. So if we have a column defined as name, which is of type string, then all data within that column name will be of type string. Furthermore, every column has a domain, a range of possible values that can appear in that column. So as an introduction of what we're going to see in the ER diagram, an entity is represented by a rectangle. It's going to have a name. An attribute is going to be attached to an entity, and it will have a name, a unique name within that entity. For example, we could have two entities with the attribute name. That's okay because they're two separate entities. But we cannot have an entity with two attributes within that same entity called name. And then we have the relationship between two entities. This is the link between the data. The relationship defines the power of the database. Now again, keep in mind, we are focusing on relational databases. Databases that support online transaction processing systems, so that the relationship is the key that links the data across the tables in the database. There's a lot of theory behind database design, much of it amazingly useful for the database architect. For the beginning DBA, the subset of the world of database theory is much smaller. Cardinality refers to how entities relate to one another. Either there is a one-to-one relationship between an entity, a one-to-many relationship, or a many-to-many relationship. For example, a one-to-one relationship. We have a table named person, and we have another table that is related to that person table, say spouse. Then there is a one-to-one relationship between the person and the spouse table. On the other hand, if we have a person table and it has an attribute email address, a person can have multiple email addresses. Therefore, the table email address may contain more than one address for any one person. That would be a one-to-many relationship between the person and the email address table. Normally, on a day-to-day basis, the cardinality will either be 0 or 1. That is, that there will be 0 or 1 entities related to another entity one or more times. This will all make sense when we demonstrate the design principles with our ER tool. So, what are we going to use as an ER tool? As an architect, as a DBA that is responsible for designing databases to support applications, we need a tool. We need something that's going to allow us to draw pictures that we can take to the developers, that we can take to the application designers, and discuss the data layout within the database. There are many ER tools, and you're encouraged to search the internet and find an ER tool that you're comfortable with, that you find easy to use, because the ER diagram itself is the same no matter which tool generates it. In our demonstration, we're going to use the MySQL Workbench 6.0. It's both a design tool, a SQL development tool, and an administration tool, all rolled into one. It is absolutely free. It's visually driven and a wonderful tool. Now, for general administration, there are many, many, many other tools. One of the most popular for web-based administration is PHP MyAdmin. And you're welcome to load this on your system and use it to administer your MySQL instance. We will not be discussing PHP admin in this course. And again, you're encouraged to perform an internet search and find other administration tools, experiment with them, find one that you're comfortable with and that you find easy to use, that provides the functionality that you need, and use it. That's what's the most important thing, is a tool that you feel comfortable using. So let's go look at some code. So now that we've got our database server up and running, we're going to install MySQL Workbench. Now we do already have client tools, MySQL Admin, the MySQL command line tool, and we can administer the server using those tools. However, this Workbench tool is an integrated environment for both modeling, SQL development, and administration. So it's a very powerful tool, and it is absolutely free. So we're going to take advantage of it. If you're installing on Windows, there are some prerequisites, and you'll have to make sure that you have these installed on your system prior to installing MySQL Workbench. We are not going to demonstrate the Windows installation because it's just click and install. And prior to doing the click and install of the Workbench, just make sure that you have the prerequisites installed on your system. We're going to install the Ubuntu Linux 12.04 version of MySQL Workbench. And I'm going to install the 32-bit version because, again, my Linux installation is a 32-bit installation. So we're going to download this. If you're not currently logged in, then you're going to need to log in, or if you haven't yet, you're going to need to create an account on the Oracle system to download this file. So the download is complete, and it is a Debian package file, so we're going to run the installation. And I can tell you beforehand that this is going to fail because of dependency issues that have not been resolved on this system. However, I want you to see these messages so that when you experience it yourself, you won't be surprised. So these are the dependency issues that exist on my system that need to be resolved. Now, typically, there is another dependency that needs to be resolved, and that is the libc template 0 library file. Fortunately, I have already installed that, so we can download that from the Ubuntu site and install it as I did. It comes down from the Ubuntu site as a Debian package, and simply run the dpkg-i, giving this package name, and it will install that file for you. Now, once you do that, you will still get these dependency issues. So we need to resolve these other dependency issues. And the easiest way to do that, again, we're not trying to be Linux administrators. So we want the easy way to make this work. We're going to say apt-get -f install without any package name. And what this command will do is resolve all of these dependencies, installing the necessary libraries to bring our system current with the dependency needs for this installation. So as you can see, after my command runs, many dependencies were resolved, more than what I had listed from the installation of the MySQL Workbench. So this is a good thing. So now I'm going to rerun the installation of the MySQL Workbench package. So I have a successful installation of the MySQL Workbench tool, and we're going to launch it in the background. And there we go. So we have now installed and are ready to use the MySQL Workbench integrated environment for developing SQL, for designing databases, and for administering our server. Now, we're not going to spend a lot of time talking about those functions. What we want to look at in this demonstration is how to use the tool to build ER diagrams. So the first thing we need to do is connect to our server. And I'm just going to call this local root, because I'm going to log in as the root. It is the local host, so we can accept all of the defaults. We're going to test the connection. I'm going to put in the root password. Everything's fine, so I'm going to connect now. I click on the connection, and boom, I am in. We're not going to talk about security now, but we are going to talk about that in this course. For right now, I'm just going to create another account because I'm not comfortable using the root account. And I'm going to make this account a DBA. So boom, now I'm going to close this connection. I'm going to create a new connection, and this time I'm going to call it course local. Boom, test connection, and everything's fine. Now we will connect using a non-root user. This is important. Again, we'll talk about security in upcoming lectures, but for now, just accept that it's important not to be root. We're back in now as a different user, and we're just going to say File New Model, and we're going to add a diagram. This is our design surface. As a database designer, as an architect, as a DBA, when you need to create a database and the structure of a database, this is where you would do it. We grab a table, an entity, and we drop it on the design surface. We double click, we get the properties of that table that we can edit. In this case, I'm just going to add a couple properties because now we have our two tables. Let's add a relationship between the tables. There we go. So now just everything is drag and drop, click and drop, and we can design our entire database using a very functional visual tool. And we can take this design and go to the developers, go to the application architect, and discuss how the database is going to support the application and show the developers how they need to interface with the data stored in the database. If you haven't already done so, install the MySQL database server and the client tools, then install the MySQL Workbench 6.0, in this case 8. These are the tools we're going to use for the remainder of the course. A database is a collection of tables. The tables, in turn, are collections of data organized in rows, where each row represents a unique record within the database. What makes this record unique is the selection of fields or column values within that record that uniquely identify that record within the database. When we talk about keys, there are candidate keys, which can be a single attribute or a collection of attributes that uniquely identify the row. There could be more than one candidate key. We select one of those candidate keys to be the primary key. That is the key that will be used to uniquely identify the row. Now, to be a candidate key, the value or combination of values that are selected must uniquely identify each row in the table, and there cannot be duplicates, because a duplicate would mean that there is not a unique quality to the key among the rows in the table. If we're building a database with tables that have relationships amongst one another, then each relationship between the tables is associated with a primary key from those tables. So the primary key becomes very important in the relational structure of the database. When we have a key that uses a single value to identify the row, we call that a simple key. On the other hand, if we have multiple values from the row that are used in a key to uniquely identify that row, that key is referred to as a composite key. In a relational database, every table should have a primary key defined. Whether that's an artificial primary key where we're generating a value as we insert into the table, or whether that is a primary key that is defined by the natural values of the elements in the table. Each table must have a primary key. A primary key does not allow duplicates, and obviously there can only be one primary key per table, and the primary key cannot be absent of value. It must have a value. Careful consideration needs to be made in selecting a primary key. Very large primary keys, that is, primary keys that either use a field that is very large or a composite key that uses multiple fields to uniquely identify the row, the length of the primary key will affect the performance of that table within the system. If our table has multiple candidate keys and some of those were not selected to be the primary key, then we refer to those not selected candidate keys as alternate keys. Again, the primary key is the basis for building the relationships between tables in the database. When we use the primary key from one table to create a relationship with another table, that primary key stored in the other table is referred to as a foreign key. The foreign key is the primary key of the table to which it refers. There's a lot of power available in using foreign keys to implement consistency and referential integrity in the database. So this is a key concept for us to understand. A primary key from one table used in another table to refer to the first table is referred to as a foreign key in the second table. We'll see this in the demonstration, and it should be much clearer at that point. Going back to relationships, if we have two tables that are related in a many-to-many relationship, then the only way to implement that in the database is to have a link table, a table that links those two other tables together based on their primary keys, so that within the link table, the primary keys from each of the tables in the relationship are referred to as foreign keys within the link table. If we have a one-to-one relationship between two tables, then there can only be one occurrence of an element that is related to the first table in the second table, where the primary key of the first table becomes the foreign key in the second table. This is what builds the referential integrity constraint in the database, that there can only be one element in a table that is related to another element in another table, a one-to-one relationship. During our design process, we can define ranges of values that an entity column can contain. These are referred to as constraints within the database. So a constraint can provide a level of business rule implementation, which limits the data that a user can enter into a table. So we can use a unique constraint, for example, to prevent duplicate values in a table. We can have, unlike a primary key, which is a unique constraint, because there can be no duplicate values in a primary key. But unlike a primary key, you can have multiple unique constraints on a table. There are no duplicates, obviously, allowed. This is a constraint that requires that all values for that column be unique. However, null, or the lack of value, is permitted. A very powerful constraint is the default constraint, which permits us, the database designer, to provide a value for a field that will be used should the user or application not provide a value during an insert operation. We can also constrain a column to not be absent a value, to not be null. So the null constraint will reject an insertion if the column on which it is defined does not either have a default value or a value provided by the user or application during the insert operation. And finally, the check constraint limits the range of possible values. Now, it's important to note the check constraint is a very powerful constraint, but the MySQL database system does not enforce the check constraint. The documentation refers to this and says that the check clause is parsed, which means it's understood by the database system, but it's ignored by all of the storage engines. That's straight from the documentation. So understanding the check constraint is important. We can provide a limit on the possible values to be inserted in a field, but it won't be enforced, at least in this version of MySQL database. We want to avoid spending a lot of time on database theory because database theory sometimes doesn't translate into pragmatic application in the database design. However, in this case, normalization does translate into good design principles. The whole point of normalization is to reduce the data redundancy within a database design. This has some great benefits for an OLTP system, an online transaction processing system, OLTP, in that it reduces storage requirements by reducing redundant data. And it increases the efficiency of the database. We're going to limit our discussion to the most prominent normalization form, which is third normal form. So we're going to take a database and we're going to go from first normal form. We're going to transition that database design to second normal form and then to third normal form. In all practical applications of an OLTP system, third normal form is generally sufficient for efficient operation of the database system. There are other forms, to be sure. These are very theoretical and we will not be discussing them. So let's go look at some code and see how to design a database and normalize that database. In this demonstration, we're going to normalize a database. The database is called school. And in that database, we are storing a table called enrollment that has information about students, courses, and grades of the students for a particular course. Recall the reasons why we perform normalization. It is for the efficient operation of the database. So when we look at this table, do we see any apparent inefficiencies? Well, unless you have experience in normalizing tables and designing databases, there probably isn't anything apparent to you in this table definition. So let's take a different approach, and instead of looking at the table design, let's look at what data might look like if we chose to use this table design. So let's go look at our database, and here is the enrollment table with sample data. So now immediately you should see that there are issues with the data within this table. For example, student ID number 1, Dana Scully, also is in another course as student ID number 8. However, in this case, somebody misspelled her name when they input it to the database. So we have a student with 2 course records in this enrollment table, but the names are misspelled. This is one of the key issues with normalization, is to resolve data inconsistencies. Also, why do we have this student information repeated in the database to begin with? It's an inefficient use of the storage space within the database to store the student name and the student birthday twice. There's no reason for this. That is what normalization is going to solve for us. Same thing with student ID number 7 and 9. Same student, 2 different names. Where else do we see repetitive data? That's the first sign to look for in a normalization exercise, is look for repeating data. Solve the repeating data and you've taken the giant step in normalizing the database. Look at the course information. The course information is also repetitive. We see chemistry class entered twice, biology class entered twice. This is amazingly inefficient. A small table with 9 rows probably doesn't matter. However, imagine a table with 100 million rows, which is not a large database, and having this level of repetitive data would waste an enormous amount of storage space. So we have two candidates now for normalization: the student information and the course information. Let's go see what normalized tables might look like for this data. The first thing that we notice is that we've now have separate tables for the students and the courses data. All of the student information, the student ID, the student name, the student birth date, is in the students table. Likewise with the course information, the course ID, the course number, and the course name are stored separately in a table called courses. So for every student, there will exist one and only one record representing that student in the database, in the students table. Likewise for the courses. For every offered course, there will be one and only one record in the database for that course, and it will be in the courses table. So what kind of relationship do these tables have with one another? A student can sign up for more than one course. So there is a one-to-many relationship with a student and the courses. However, a course can have many students assigned to it. Therefore, there is a many-to-many relationship between the students and the courses. And recall from a previous discussion that to implement the design for a many-to-many relationship, we must use a link table. So we've created a student course link table. This table has a link ID, has the student ID and the course ID, and the rest of the data associated with a particular student and course, namely the grade information. Notice that the student ID in the student course link table is the same student ID from the students table. By definition, because we use the primary key from the students table as a key in the student course link table, within the student course link table, student ID is referred to as a foreign key. Likewise for the course ID, in the student course link table, we use a course ID to identify the course from the courses table. Course ID is the primary key in the courses table. Therefore, in the student course link table, course ID is a foreign key. To define a foreign key using the MySQL Workbench, we go to the Foreign Key tab. We enter a name for the foreign key. Now, as a convention, we put _FK to identify this identifier as a foreign key. So I've created a foreign key, student ID _FK, that references the students table. Which field does it reference in the students table? It references the student ID field. Likewise with the course ID. The course ID foreign key references the courses table. Which field in the courses table? It references the course ID field. As soon as you define these foreign keys, the MySQL Workbench will automatically generate the necessary relationships between the tables in the ER diagram. Now again, we're not concerned about how to create the tables, the SQL code for creating the tables at this point. We will cover this in the course, but not now. What we're concerned with now is normalizing the tables. So we have now isolated the student data. There will be no repetitive student data. There is nothing in the student table that is dependent on any other data, and likewise in the course table. We've isolated the course data in the courses table and we've removed all repetitive data, and there is no dependency between the data. Therefore, we can say that this database is normalized. There is an argument for moving the grade data out of the link table, creating a grade table that would remove the redundancy of the grade data as well as the dependency that exists within this table on the grade data. We're not going to do that. We're not going to carry the normalization to that next level. You could do it and it would not be wrong, but in this example, we're not going to take that next step. We are satisfied that the database is now sufficiently normalized to reduce the dependency between the data of the students and the courses, and to reduce the repetitiveness of the data within the database. So let's go look at some sample data and see how this looks now in comparison to our original enrollment table. So recall that this is what the original data looked like stored in the enrollment table. Now we have our course data in the courses table, and each course gets one row, one record in the table identifying that course uniquely. Likewise with the students, every student gets one record in the table. Every student is uniquely identified by one record in this table so that there are no more repetitive student names or student birth dates. And we can be assured of data consistency for both the courses and the students. So how do we link all this together? Well, here's our link table. So we have a student ID, a course ID, and the grade assigned to that student for that course, and the date of the exam when that grade was recorded. So we have student 1 in course 1 received a letter grade of A with a total grade score of 99 on December 15th, 2012. So how do we know who this is? Well, we go to the course table and we see the course ID was Chemistry 1 and student ID 1 was Dana Scully. So looking at the link table, we can say Dana Scully got an A in Chemistry 101. Likewise, student 2 in Chemistry 101 also got an A. Student 2 in course 2, which is Biology 101, got a B. So this structure, this link table allows us to pull the data from both the student and the course tables and bring them together very efficiently in the link table. In this demonstration, we're going to continue with the normalization of the school database, this time focusing on the instructor information. So the instructor assigned courses table contains information about the instructor and the course to which the instructor is assigned. As we demonstrated in the previous example, there are immediate candidates for normalization. We're going to separate the instructor data and the course data as our first step in normalizing this information in the database. To do that, we're going to click on Add a Table. Double-click then on the table in the design space. We're going to give it a name, in this case, Instructors, and we're going to assign the columns. So we're going to give it an instructor ID column, then an instructor name column, then a department name column, and the instructor's level. Let's fix this typo. And so now we have our instructors table. This is all of the information that will uniquely identify an instructor. Let's do the same thing with the courses. So we're going to click on Add a Table, drag it onto our workspace, double click, and we're going to call this table Courses. We're going to give it an ID field, course ID, course number, and course name. Now we have our Courses table, which will uniquely identify every course individually that is being offered, and we have our instructors table with records that will individually uniquely identify every instructor. So what is the relationship between these tables? Can an instructor be assigned to more than one course? Absolutely. Can more than one instructor be assigned to teach a course? Absolutely. However, in our example here, we're going to place the limit that only one instructor can be assigned to teach any one course, but that an instructor may be assigned to teach more than one course. So that is a one instructor to many courses relationship, a one-to-many relationship. So how do we define a one-to-many relationship between these two tables? The easiest way to do it, using the tools within the MySQL Workbench, is to come back to the Courses table and click on the Foreign Keys tab. Because the way that we're going to link these two tables and identify that relationship is by including the instructor ID value for the course to which the instructor is assigned. So we're going to click on the Foreign Keys tab of the Courses table, and we're going to enter the instructor ID FK for foreign key to identify this foreign key relationship. And the table that's going to be referenced is the instructors table. And notice that immediately our Workbench tool drew the relationship between the instructors and the course table as a one-to-many relationship. Now that we've defined the foreign key, let's define a column to store the instructor ID value, and we can assign that column to our foreign key. And notice that, again, this has been automatically defined for us by the Workbench tool. If we look at this diagram now, with the instructors and the courses tables, we've gone from this denormalized or flat table into these two tables that are somewhat normalized. Now you can look up the definition of the different forms of normalization, and we can have a formal discussion about whether or not these tables are in third normal form or second normal form. So the easiest way to know that you're done with normalization, to see if there is no more repeating data in the tables. So in the courses table, there is no more repeating data. However, in the instructors table, the department name is going to be a repeating data value. There will be multiple instructors assigned to a single department, and so for each instructor entry in the instructors table, that department name value will be repeated. We're going to pull that data out of the instructors table by creating a new table, and we're going to call this table departments. And departments is going to have an ID field and a department name field. So now we've defined the departments table, and we're going to modify our instructor table So we've changed in our instructors table, we've changed department name to department ID, and we're going to define a foreign key for that field on the department ID primary key in the departments table. Notice again that the Workbench tool automatically drew the relationship for us. So now we've reduced repetitive data in the instructors table by using a lookup table called departments. So we could do the same thing with level and reduce the repetitiveness of that data as well. If we assume that there are two levels of instructor, master's level and PhD level, so we could create a new table called levels that would have the level name and an ID. Then again, going back to our instructor table, we could change the level field to a level ID and then again define a new foreign key for the level ID. And notice again that our relationship was automatically drawn for us. So in the end, we have completely normalized this design. We've started with a flat or denormalized table, and we've now gone to a four-table design for this database for the instructors and their assigned courses, and we've completely reduced dependencies and repetitive data within this part of the database. We've seen how important the table structure is to the efficient operation of the database. What's also very important is how we choose to store that data within the tables. MySQL database system provides many different data storage types for our use, and we need to understand the differences between those types so that we can make informed decisions about how to store our data. The general categories of data are collections of characters or strings, numeric data, and another very important data type within the database, dates and times. There are many different string storage types provided by the MySQL system. We can store characters using the char type. This is a fixed length type whose size must be defined and cannot be exceeded in the table. A varchar is a variable length character with a maximum defined size. We also have text types, tiny text, text, medium text, long text, and binary large object types. Now, when would we choose one type over the other for storing a string? Char type is a fixed length data storage structure. Each character in a string is represented by a single storage byte. So when we declare a char of size 15, we will use 15 bytes of storage regardless of how much actual data is stored within the char type. So this can be inefficient for storing string types with variable lengths. In contrast, the varchar can be defined with a maximum length. However, it adjusts its storage utilization based on the size of the string that's stored within that varchar type. So in our example, the string Bob, B-O-B, would only use 3 bytes of storage for those 3 characters. It's a sharp contrast to storing Bob in a char 15, where only 3 bytes of storage are actually used for the data, but the column data type is declared to use 15 bytes of fixed storage. So there would be 12 bytes of wasted storage. Again, in a large database, this kind of inefficient storage adds up quickly. Now, there is overhead in the use of the varchar type. because the system must keep track of what's being stored within that type. So there is overhead associated with the varchar type, something around 1 to 2 bytes of overhead. Again, there are trade-offs for the use of the varchar versus the char type. We'll reduce disk space utilization because the varchar will adjust itself based on the length of the contents. However, manipulating the contents of a varchar becomes problematic because we don't know how much data is actually stored within it. Whereas if we used a char type of fixed length, then we could do any kind of string manipulation against that fixed length storage structure. Experiments have shown that index searches are about 20% faster on a char type versus a varchar type. So this again is very important to keep in mind, that a simple decision such as what type of data storage am I going to use for a string will significantly impact the performance of the database. And we start adding these performance hits up cumulatively, we can significantly impact the performance of the database. Bad table design, poor choice of data types, and other factors that we're going to investigate as we move forward can yield amazingly poor performance in the database. Now, for date types, which are amazingly common in a database and are used very frequently for range searches, we have 5 different storage options. A date type, which simply stores the year, month, and day. A date time, which stores both the year, month, day, and the hour, minutes, seconds. A timestamp, a time, and a year value. Notice the permitted values for these data types and their storage requirements. So let's go look at some code. In this demonstration, we're going to look at designing a table named contacts and the data type choices that we have to make in designing this table. So the first field I want to add is first name. And we have to decide now which data type to use. We have a choice. We can use a char and have a fixed sized data type, or a variable char, varchar, have a variable length data type. Then if we choose, as we should, the varchar type, what is the maximum size that we want to set for that varchar? A quick internet search of first name length would suggest that the maximum length for a first name is about 11 characters. So we're going to choose to make our varchar 15. Give us a little padding above the 11. And then we're going to have last name, another field. Now this one, again, we can use a varchar for a variable length type, or we can use a char, which is, again, a fixed length type. There's a recent story about a user whose last name did not fit into a database, and that last name was 35 characters in length. Therefore, to be safe, we're going to leave the last name at the default value of 45. We're going to use the variable character with a maximum length of 45. Next, we want to store a contact's email address. Our choices are fixed or variable length fields. In this case, 45 may not be enough depending on the email address. So we're going to up this to 50. Then we're going to store a phone number for our contact. Now the phone number is an interesting problem. If we assume, after discussions with the business analyst and the developers, we've agreed that the phone number will be 10 digits in length, an area code, a 3-digit prefix, and a 4-digit body number. So Do we really want to use a variable length character in this case when we know that the phone number will always be 10 characters in length? I would argue no. And so we're going to change this to a car 10. Now, how about street address? This would include the numeric value for the street address, the street name, and whether it's a street, a drive, a circle, boulevard, and so on. So this storage location may need to be pretty well sized. On the other hand, it could be very small or null. So we don't want to waste space, and we will not use a fixed length type. We will use a varchar. We're going to increase the size to 100. How about city? Well, again, a simple internet search will reveal that the longest city name in the United States is 48 characters in length. And again, after discussions with the business analysts and the application developers, it's been agreed that the domain of our contact information will be restricted to the United States. So knowing that the maximum city name length is 48, we're going to use a varchar, but we're going to increase it to 50. So we're going to have a maximum size of 50 in our varchar storing the city name. How about state? We've discussed this with the business analyst and with the application developers, and we've all agreed that the state will use the standard post office 2-letter abbreviation for states. So do we need a varchar? Absolutely not. We know that the state data will be fixed length at 2. So we're going to change this to a car 2. We're going to add a zip code field. And again, after discussions with the business analyst and the developers, we've agreed that the zip code will always be 5 characters. Use the postal 5-digit zip code. So we're going to change this to a car 5. And we're going to have a switch for all of the records to identify whether or not the contact is active. So this is a yes or a no, a true or a false, a 0 or a 1. So what data type can we use that is the smallest, most efficient for storing either a 0 or a 1 or a true or a false? Well, let's look at our choices. We have a Boolean type. We have a bit type. Now, this is where a fundamental understanding of the data types is important. A Boolean is really just a tiny int, which is 1 byte. However, a bit, which will store a value of 0 and 1, is more efficient. We're going to choose for a data type for our active switch in this table as a bit 1 field. We've decided to store a photo of the user in the table. Storing the actual photo in the database is not recommended. So we're going to do this just for this example. If we chose to store the actual photo in the database, which again is not recommended, then we would choose a blob data type for that storage. The more appropriate approach for storing the photo would be to store a path to the photo. So a string representing the path to the directory and the name of the photo within that directory that's associated with the contact, rather than storing the actual photo in the database. But again, to demonstrate the breadth of available data types, when we're designing a table, we're choosing to store the actual photo within the database. So here's our table now. This is a space-efficient design for the data types in the table. We're not using space we don't need to use. We've made selections between variable length and fixed length character types. And we want to add a date field to represent when the contact was added to the table. So we're going to call it insert date. Now again, there's different data types. We have date, date time, timestamp, time, and so on. So which one do we want to use? Do we really care that the insert date is anything more than a day? So a year, month, day representation. Do we need to know the time that the insert occurred? The difference being 3 bytes to store a date versus 8 bytes to store a date time. So we go back to the business analyst and to the developers and we have a discussion. Do we need the time, the exact time when this record was added to the table, or is the date sufficient? We come to an agreement that the date is sufficient, so we choose to use the date type. We have a very efficiently designed table with respects to the data storage types. Now, obviously, this table could be normalized. We haven't done that. This example is strictly about data types. So yes, we can further normalize this table, and one of the immediate normalizations would be to remove the state value into its own table, and instead of storing the actual state value, the 2-character state value, we could store a tiny int, a 1-byte value that represents the ID in the state table. There are only 50 states. We don't need a 4-byte integer to store 50 values. So we could use the tiny int, and that would save us 1 byte. The issue here isn't thinking small. The issue here is thinking that your database will grow to millions and potentially hundreds of millions of records. So when you're making the decision now to save 1 byte of storage for the state value in the future with 100 million records, you've saved 100 million bytes of data storage space. So these are the trade-offs that as a database designer we make in selecting data storage types for our variables. We have to be cognizant to use the space available to us in the most efficient manner possible. So we've seen the benefits of normalization of our database design. Remember that the primary function, your focus as a database designer, is to structure the data within the database in such a way as to allow fast retrieval of that data and to minimize data inconsistency within the database. Remember that your decisions during the design process have a profound impact on the future performance of the database. And making changes once you're in production to the structure of the tables within the database is painful and difficult. Our use of appropriate data types ensures the efficient utilization of the available storage for the database. And as we've seen, the MySQL Workbench tool is an excellent ER diagramming tool and provides, as we will see, the ability to single-click forward engineer our design into the database implementation. Remember the ACID principle: atomicity, consistency, isolation, and durability. This is a foundational principle of all database systems, if those database systems want to claim that they protect their data. So what we're going to do now is look at how MySQL implements the ACID principles. Atomicity in MySQL is provided by implicit and explicit transactional support within the system. A transaction is a collection of SQL statements. If those SQL statements are executed, they must all execute as a unit to completion, or the entire collection of SQL statements gets undone or rolled back. So it's an all or nothing proposition for the SQL statements within a transaction. A transaction has a lifespan from the beginning or the start of the transaction through the commit of the transaction, the completion of the transaction. Once the transaction is committed, any changes that those statements within the transaction made to the database become permanent. If at some point between the start and the commit of the transaction, some error or other condition occurs that prevents the transaction from committing, all of the statements up to that point are rolled back so that the database is returned to the state it was in prior to the start of the transaction. Now, in MySQL, the default is implicit transactions or auto commit, so that if we submit a batch of SQL statements, there will be an implicit start of the transaction and an implicit commit of the transaction embedded within those SQL statements. Within MySQL, we can also set save points. So at some point within the collection of SQL statements within a transaction, we can set a save point and say everything is fine up to this point. If an error or some other condition occurs prior to the completion of the transaction, we can roll back the transaction to that save point rather than having to roll back the entire transaction and then do some other function to either recover from the error or commit the changes up to the save point. So we have save point management keywords, setting a save point with the save point keyword, roll back to save point, and release save point. Now, it's important to note, as we've said when we discussed the different storage engines, that transactional support is only provided in the InnoDB storage engine. So let's go look at some code. In this demonstration, we're going to talk about transactions. In doing that, we're going to use the Sequila sample database that's available on the MySQL website. Specifically, we're going to use the film table from that sample database. Before we look at any of the transaction control keywords, let's check on the session variable auto commit. Now, the session variable is specific to this connection. We're going to execute show session variable, and we're going to ask to see the auto commit variable. And as you can see, the auto commit is currently on. So we're going to turn that off by executing set auto commit equals 0. Now we can see that we have turned off the auto commit. Now again, this is session only. This is not the global setting for the auto commit variable. If we want to set the auto commit globally for the server, we come to the administration section, system variables, and we can change the value of auto commit for the entire MySQL instance here by saying on or off. Now the default setting is on. I've already changed the auto commit system variable to off. So let's look at the value of a record in the film table. And we're going to look at film ID 52 with a title of Ballroom Mockingbird. The first thing we're going to do is update the title of the film using an incorrectly spelled title. Now notice that we did not execute the rollback statement. We started the transaction, we executed the update statement, but we have not executed either commit or rollback. So the transaction is open and the value has been changed only from our perspective. this connection's perspective. This connection uses the user course local. So I'm going to switch to the local root connection, and I'm going to select the same film ID 52, and notice that the title has not changed. It is still Ballroom Mockingbird, even though from our perspective, in our connection with the open transaction, we see Ballroom Mockingbird. So now if we come back to our code and commit the transaction, so now we have told the database system this transaction is complete. Make these changes permanent. If we go back to our local root user connection and run this select statement again, we see that now the permanent change of the title of Film ID 52 has been recorded in the database. At this point, there is no going back. The change has been made. It's been committed to the database. So we could run rollback at this point and it will do nothing because the change is done. The update is completed and it's been committed. On the other hand, should we now choose to correct this error by changing the title to Ballroom Mockingbird for, again, the same film ID 52, we're going to run this transaction, and within our connection, our session as this user, we see the change, Ballroom Mockingbird. However, going now to another connection, a distinctly different connection by user local root, if we run the select statement, there has been no change to the database because the transaction is open and uncommitted. But from our perspective, our user perspective in this connection session, we see the change. But we've decided not to commit this change. So we're going to roll back or undo the change to the database. So now, from our perspective, the value of the title goes back to the prior value, and from the other connection's perspective, nothing changes. The key to explicit transaction control in MySQL is the start transaction command followed by one or more SQL statements, followed by either commit to make the changes permanent in the database, or a rollback statement in the case of a failure of one or more of the SQL statements to undo any of the other changes that the collection of SQL statements might have made to the database. So we start a transaction and we commit a transaction, and the commit is the end of the transaction statement. Data consistency in the MySQL database system is provided by the locking mechanism that's implemented by the different storage engines. In the InnoDB storage engine, we are provided with row-level locks. And in the MyISAM storage engine, we're provided with table-level locks. The locks ensure that if one transaction is working with some row of data, that no other transaction can access that data while it is being changed by the first transaction. Recall also that a database is made up of tables. The tables are made up of rows. The rows are made up of columns. The columns contain the data. So when we talk about row level versus table level locks, we can support a higher level of concurrency, that is, multiple transactions accessing the same table at the same time, when we use row level locks rather than when we use table level locks. So the row level locks are significantly more efficient and provide a higher level of concurrency in the database. Typically, locks are managed by the database engine, by the storage engine itself. However, we as developers can take control of the locking during the execution of our transactions. This is not a good idea. In general, we should allow the locking mechanism to be managed by the storage engine. Now, since we're talking about locks, what happens when multiple transactions are competing for a set of locks within a table or a database? If transaction A is holding a lock and waiting for another lock, and transaction B is holding that other lock, waiting for the lock that transaction A is holding, then transaction A is waiting for transaction B, and transaction B is waiting for transaction A, and we have a situation referred to as a deadlock, where two transactions are waiting on each other to release resources. This is an amazingly common issue, and many of the occurrences of deadlocking can be traced back to poor programming practices. Now, how do we resolve deadlocks? Well, typically we don't resolve the deadlock. We try to program our SQL statements, our transactions, in a way that prevents or minimizes the occurrence of deadlocks. But once a deadlock occurs, the MySQL system has a process that runs within it to detect the deadlock. Once that deadlock is detected, the MySQL system makes a decision and terminates one of the transactions in the deadlock. How does it decide? Well, typically the easiest way to decide is to determine which of the transactions is the least expensive to roll back. So if transaction A has made fewer changes to the database than transaction B, then transaction A will be selected as the deadlock victim, rolled back, and terminated, thus freeing the deadlock and allowing transaction B to continue with its processing. Isolation in the MySQL system is provided by the isolation levels defined within the MySQL system, so that we can define how isolated transactions are from one another. There are 4 isolation levels provided by the MySQL system: serializable, repeatable read, read committed, and read uncommitted. These all have trade-offs. We need to understand what those trade-offs are so that when we decide which isolation level is appropriate for our application, we'll be making an informed decision. So these are the conditions that isolation helps prevent: phantom reads, non-repeatable reads, and dirty reads. And the chart defines how each isolation level responds to or provides protection from each of these 3 data issues that can occur when inappropriate isolation levels are used. Depending on your application, the isolation level will guarantee that if you run a transaction, that within that transaction you read a row of data twice for some reason, that within those 2 reads inside of that transaction, the data that you get returned will be the same, so that no other transaction or insert statement can change the values while your transaction is executing. This is the foundation of isolation within a database. So for durability, MySQL uses a binary log to record what the MySQL database system refers to as events within the database. An event is anything that occurs within the database that has an impact on the data. Binary log gets written to disk, and all transactions that occur on the database are recorded in that log, so that if there is a failure, the binary log can be used to recreate those transactions to put the database back in its correct state. Now, it's important to note that you are writing to the disk with the binary log. Therefore, that write operation uses resources, and that costs performance. However, to get the durability, the data safety, so that we can protect the state of the database, that performance cost is far outweighed by the benefits of binary log recording all transactions within the database. So let's go look at some code. In this demonstration, we're going to examine isolation levels and locking. Isolation levels are important to understand because they have significant impact on both data consistency and potentially the performance of the server. So to check the current setting of the server at the global level, we can execute the show command, global variables. We're going to use the like keyword and then two wildcards. The % says to match any string that contains the word isolation. It may start with 0 or more other characters, and it may end with 0 or more other characters. So show us the global variable that contains the word isolation. And so in the result, we see that the current isolation level is set to repeatable read. And we can change that setting by using the set command. We're going to say set global transaction isolation level, and then which level we want to set it to. In this case, we're going to set it to read uncommitted. And now we can check and see that we've changed the global value at the server level. We've changed the value to read uncommitted. And likewise for repeatable read and serialization. So what does read uncommitted mean? If we have two transactions, transaction A and transaction B, if transaction A is reading, selecting from a table, while transaction B is changing data in that table, the same data that transaction A is reading, transaction A will read the data changed by transaction B, even though transaction B has not completed. It has not committed the data. Transaction A will still read that data. Now, read uncommitted can cause data consistency issues. However, it allows the highest level of concurrency in the server. That is, many transactions can be reading from tables simultaneously without the risk of being blocked by a lock caused by a transaction writing to the table. Read committed, on the other hand, is restrictive. It will not return data that has been changed by another transaction until that data change has been committed. Repeatable read will return the data that was read regardless of whether or not that data was changed by another transaction. So for example, I have transaction A that does a select on a row in a table. Transaction B makes a change to that row that transaction A just read. Transaction A does some other work, then reads that same row again. In the meantime, transaction B has made a change to that row. Transaction A will get the same data it read with the first select statement, regardless of whether or not transaction B has committed its update command. Serializable, on the other hand, is the most restrictive isolation level. If transaction A is reading and writing to rows in a table, all of those rows, both those being read and those being written, will be locked so that no other transaction can access those rows. Two side effects of serializable: many locks, both read and write rows get locked, and transactions that are just reading data that is also being read by transaction A are blocked. They cannot read that data. Even though it's not being changed, they cannot read it until transaction A commits and releases its locks. Using the serializable isolation level has the potential of causing serious performance issues on the server because of the decrease in concurrency and the increase in lock management. So let's see how all of this plays out with some queries. So I've created two connections. I have my local course connection and I have my local root connection. We're going to use the same data we used in the previous demonstration, the Sakila film table, and we're going to be looking at film ID 52. The current value of film ID 52 has 3 L's in the misspelling of ballroom. So we're going to go to local course connection and confirm that we're looking at the same data, 3 L's in the misspelling of ballroom. Now, let's change the isolation level in this session for this connection only. This has no effect on the global server setting. So for the life of this connection, we're going to change the isolation level to read uncommitted. Currently, the isolation level is read uncommitted. So we're satisfied that we're going to be reading uncommitted data. And now we're going to update the film table for film ID 52, and we're going to update it with ballroom mockingbird, with ballroom misspelled this time with 3 A's instead of 3 L's. And we're going to do this within a transaction. We are not going to commit the transaction, so the transaction will be open uncommitted when we run this code. So let's run it. So now there is dirty data. There is an uncommitted update of the film table for the row film ID equals 52 that changes the title from BALLL room to BAAALL room. So what are we going to see when we go to our other connection and read this data? Well, let's make sure that this connection is set for the proper isolation level. See, now in this connection, our isolation level is set for repeatable read. It will not read that uncommitted data. So we're going to change the isolation level to read uncommitted. And let's double check and make sure that that happened, and it did. When we read the film table with row ID 52, the original value was BALLL room. The changed value, BAAALL room, has not yet been committed by transaction A. So when we run our select statement, we see the uncommitted value from transaction A because our isolation level is set to read uncommitted. So in many applications where data inconsistency is not an issue, performance can be greatly improved on the server by setting the isolation level to read uncommitted. But again, be careful because this means that you're going to see data that will potentially be rolled back by the transaction that's updating that data, and you've read it before the commit on that transaction. Again, this is application dependent. In some cases, this works very, very well to satisfy the requirements of the application and provides a level of performance that cannot be matched by the other isolation levels. If we change our session isolation level to read committed, let's confirm that we did read committed. Now our transaction in our other connection that's updating the title to BAAA LL room has not committed. So the data is not changed in the database until the commit command is executed. So now we're saying from this transaction, read only the committed data. What's the committed data? Well, it is the data as it existed before this transaction executed. So what we should see here is the original value of the title, which is 3 L's, LLL. So that's read committed, which only returns data whose changes have been committed to the database. So now if we run the commit command in our local course connection, we have actually changed the data. And if we go back to our local root connection, where we previously had just read the 3L version of the title, now that the local course connection has committed its update, we should see the 3A version of the title. And so if we run our select statement again, we can confirm that indeed now we are reading the value that was committed by the local course connection. So in review, uncommitted and committed transaction isolation levels have significant differences in the way that data inconsistency is treated. Serializable is the most restrictive isolation level and will impact performance by increasing the number of locks and reducing concurrency. And repeatable read guarantees that if within a transaction data is read twice and somewhere in the middle of the two reads, another transaction changes that data, the second read will return the same data as the first read, regardless of the committed or uncommitted changes made by the other transaction. So we've changed the isolation level now in both connections back to read committed. And what we're going to demonstrate is the locking mechanism. We're going to try to update the same row in both connections. We're going to start this transaction in the local course connection, and then we're going to start this transaction in the local root connection. And if we look in our status window, we can see that the local root connection query is running. It's running because it is blocked by the lock on the row that was obtained by the local course connection when the update statement was executed, and it's not yet committed. So the local root connection is blocked by the lock. So let's commit this transaction now, which will write the data to the database permanently and release the lock on the row. And we can see that we waited too long to commit our transaction because our lock wait time expired. We were locked out of this row longer than the permissible timeout period that is set on the server. So in the InnoDB engine, the locks are obtained at the row level. So we could have had other transactions accessing data in this table, and the only transactions that would be blocked would be the transactions that were attempting to access data on which a lock had been placed, because we're dealing at the row level. Now, the locks can be escalated. If necessary, a table lock can be obtained for an update statement. However, if you lock the entire table to do an update on a single row, then you have significantly impacted the performance of the server because no other transactions can access that table so long as you hold that lock. So we try to keep the locks at the row level. It is one of the advantages of the InnoDB storage engine, that it uses row level rather than table level locks. Lastly, we want to look at the binary logs. These provide the durability of the InnoDB storage engine. By default, the server will not be using binary logs. So if you see this error when you run show binary logs, it's because the binary logging system has not been initialized in the server. In order to configure the server to write to the binary log, we need to start it with the log option. So I've stopped my server with the stop command, and now I'm restarting it with the --log--bin command. And this is going to initialize a binary log for the server. So now, with the binary logs being written by the server, if we run the command show binary logs, we get the list of the 4 log files that have been recording the events in the system. And when we discuss server maintenance, specifically backup and recovery, we'll see the value of these logs. Where are the logs written? Well, this also is controlled by the my.cnf file. And within that file, a configuration setting can be provided that defines the location of the log files. In the case of this server, the log files are being written to the same directory as the data files. However, your server can be configured to write the binary logs to any directory that you choose. So to summarize the ACID support provided by the MySQL database system, in the InnoDB storage engine, we have implicit and explicit transactional support with the start transaction, commit, and rollback keywords. We also have the ability to save partial transaction execution with the save point and the rollback to save point and release save point keywords. In the InnoDB storage engine, we also have row-level locking that protects the data consistency within the database. And to protect against dirty reads or phantom reads or non-repeatable reads, we have isolation levels that we can define for our transactions within the MySQL database system. And for durability, we have the binary log that records all of the database changes and allows us, if there is a failure of the system, to recreate the state of the database by replaying the contents of the binary log. So the ACID support within MySQL is well supported by the features of the InnoDB storage engine. As database administrators, we have three primary responsibilities: the security of the database, maintaining and optimizing the performance of the database, and protecting the data stored within the database from system failures. We're going to examine each of these responsibilities and demonstrate what it takes to accomplish them in the MySQL environment. The primary characteristic of the MySQL database system, which makes it the most popular open source database system, is its ease of use. That ease of use is carried forward into the mechanisms for maintaining the database performance. MySQL provides three commands to maintain the integrity and the performance of the tables within the database. The check command validates the integrity of the data stored within the tables. The optimize command ensures the optimal performance of the table, as does the analyze command. In fact, the optimize command calls the analyze command as part of its process of optimizing the performance of the table. The most important thing to take away from this is how easy it is to maintain the data within a database using the MySQL database management system. Now, one of the most important responsibilities for the DBA is data security, ensuring that the data that we put in the database can only be accessed by authorized users, and that those authorized users can only access the data that they are permitted to access. Now, database security is not solely the responsibility of the DBA, because security is a principle that must exist in all levels of the IT infrastructure, from the database to the network to the server. Therefore, to ensure the security of our MySQL database, we have to work in concert with others. So assuming a user has an account to get on the server, that would be step one. A user has an account to log into the server. Then the DBA creates a MySQL account to allow that server user to log into the MySQL database system. A username for a MySQL account can have a maximum of 16 characters, and every account that's created must have a password. As DBAs, we need to ensure that a database user only gets access to the data that that user needs in order to accomplish their job. No more and no less. So we have the ability within MySQL to assign privileges either at the server level or at the database level, at the table level, and even down to the column level. So let's go look at some code. In this demonstration, we're going to examine how to create a user and limit their access to a database. We're also going to look at some basic table maintenance functions necessary to ensure the optimal performance of the database. Well, first, let's take a look at what users currently exist on our system. To do that, we're going to query the MySQL database's user table. And when I run that query, I'm asking for all of the information in the table. I see that I have two users, my course user and my root user. The only two users on the system, and both of them have full permissions on the system. So now we're going to create a database user and limit that user to a specific table on the database. So first we're going to create the user, and I'm calling this user limited underscore local. The host from which this user will log on to the database is the local host, this server. And I've identified a password for this user. So let's run this and now look into our user table again, and we can see that we have a new user now, limited local. Now we have not granted any permissions to this user. So let's grant the select permission. So the keyword here is grant. And what permissions are we granting? Well, in this case, we're going to permit this user the select permission on the Sequila database, but only to the film table. So let's execute this. Once we've changed the permissions for a user, we must flush the privileges from the system, forcing the MySQL security process to reread the permissions table. So let's flush, and now let's log in as that user, limited local. And I'm going to select from our film table. If I try to update this film table or any other table in the database, that command will fail because limited user does not have the update permission on the table. So our permission set for the limited local user only permits selection from the film table. No other SQL commands can be executed using that account. Well, let's create an unlimited user now. So again, create keyword user, the name of the user, the @ sign, and the host from which the user will connect to the database. The keywords identified by followed by the password string. So we're going to execute that. Now we're going to grant all. Grant keyword all, identifying all permissions, that is select, update, insert, and delete on every table in the Sequila database. And again, we need to flush the permissions to force the security subsystem to reread the privileges table. So now this account has complete access to any of the data on the Sequila database. So now let's create yet another user. And this user is going to be somewhat limited, and the login is going to be permitted only from the local host, this server. And again, I've provided a password for this user. The permissions we're going to grant to the user are limited to the select and the update SQL commands, but those commands can be executed against any table in the Sequila database. And we're going to flush the permissions. I'm going to run these three as a group. And so now we've created the somewhat limited user. That user has select and update permissions on the Sequila database. So now let's take a look at the user table, and we can see our three new users listed in the table. None of these users have any server level permissions. There's only two new keywords to create a user and to define permissions for that user. We create a user and we grant permissions for a user. Now, to drop a user, we use the keyword drop. Drop a user and the name of the user. So we're going to drop our three new user accounts and flush the privileges. If we look at our user table again, we'll see that the users are no longer listed in the table because we have dropped them. Routine maintenance of the database is essential to ensure the performance of the database. So we're going to look at commands that help us to optimize the internal storage of the data within the tables in the database. So first, let's look at show table status. This is a command that's available that provides us information about the data in a table. In this case, the film table. Now, it should be noted that show table status is notoriously incorrect in the statistics that it reports. Accurate or not, it does provide statistics on the table. The integrity of the table and the rows of data stored in the table must be routinely checked, and if errors are found, those errors must be corrected to avoid large-scale corruption of the database. We do that by executing the check table command, and in this case we're going to limit it to a single table. We're going to check the film table, and what this does is look for corrupted data pages within the table storage structures, and for this table the check returned an OK message. The integrity of the database must be checked regularly to avoid large-scale corruption of the internal data. The next command is analyze table, and this command is going to recreate the statistics on the key values stored in the table. The command runs and reports that it ran successfully. What this does is it recalculates the statistics, the distribution statistics that are used by the query optimizer to develop the execution plans for the queries. This is incredibly important because it allows the query optimizer to use the most up-to-date statistics when developing the query plans. Optimize table goes a step further. Recall that earlier we said that optimize table calls analyze table as part of its process. Some of the other things that optimize table does is releases unused space. So we're going to execute this. The error message, table does not support optimize. Doing recreate plus analyze instead is absolutely normal. What the InnoDB storage engine does to optimize a table is drops the table, then recreates the table, and runs analyze to create the key statistics for the table. This ensures that the table pages on which the data is stored are optimized and that the key statistics are fresh on the table. These three commands, check table, which validates the integrity of the internal data storage structures of the database table, the analyze table, which recalculates the key value statistics on the table, and the optimize table, which repacks the data pages. So it reorganizes the data within the internal data storage structures and then recalculates the key value statistics by calling analyze table. These three commands are vital to the maintenance of the database and should be executed on a regular schedule against the database. In addition to our responsibilities for database security and performance, as DBAs, possibly our most important responsibility is to protect the data contained within the database from some kind of failure. And when we talk about failure, this could be a server failure at the hardware level. It could be a server failure at the operating system level. It could be the corruption of the MySQL instance. No matter what the failure is, we as DBAs must ensure that the data within the database is safe and ready to be reconstituted either on a backup server or on the production server after it's repaired. To protect the data, we perform backups of the database. And a backup can be done either logically or physically. When we do a logical backup, the MySQL system generates SQL files that will reconstitute the database. These files can be generated while the database is online and have the advantage that they are machine independent, which means you can take these SQL files and execute them on a standby server to reconstitute the database and not be concerned that the configuration of the recovery server is different from the configuration of the failed server. Another approach to backups is simply to copy the physical data files at the operating system level. This is much faster than the logical backup and allows for a faster recovery time with some assumptions about the configuration of the server. When we're performing a logical backup, we can choose to do a full backup of all of the data and objects within the database. And once we have a full backup, we can then choose to do incremental backups, which only record the data that has changed since the last full backup. Now, the limitation with the incremental backup is that it does require the use of the binary log. So in the worst case scenario, we've had a physical server crash. Either the hardware or the operating system has failed and we need to reconstitute the database on a backup server. In designing our backup strategy, we need to not only take into account how long it takes to perform the backup, we also need to take into account how long it takes to recover from the failure. With this consideration, the physical backups are a better solution because they have a very low recovery time. Again, there are assumptions about the configuration of the server from which the backup was taken and onto which the backup is being restored. The logical backup requires that each of those scripts that were generated during the backup process be executed on the recovery server. This can take a good bit of time. As the core of the business, the database downtime must be minimized. When we do a full recovery, we put the database back into the state it was in at the time of the last full backup. If we're using incremental backups, we would recover with the full backup and then apply the incremental backups. And we can, with those incremental backups, recover to a point in time. So let's go look at some code. In this demonstration, we're going to examine how to perform database backups using the MySQL dump tool. We're going to do this with the understanding that there are many open source and fee-based backup tools that are available to assist us with automating the backup process for our MySQL databases. We're going to focus on the native tool MySQL dump. We use this command at the Linux prompt, passing a username, the -p for the password prompt, and then a switch. In this case, we're saying -- all databases. So this is going to take a full server backup, and we're pumping that backup into a file called fullserverbackup.sql. So when we run this, the MySQL dump tool will generate the drop and create SQL commands, all of the insert commands, every SQL script necessary to reconstitute all of the databases in the system. If we want to limit our backup to a single database, then we can pass the database name and pipe that into a file. In this case, we're backing up the Sequila database, and we're putting those backup scripts into a file, sequilabackup.sql. We can also selectively back up tables within the database. So in this example, we're going to back up the Sequila film table. We're going to put those generated backup scripts into the Sequila film backup.sql file. We can also back up selective databases. So in this case, using the MySQL dump switch databases, -- databases, we can list the names of the databases that we want to back up, then pipe those backup scripts into a file. In this case, we're backing up the Sequila and the world databases, and we're putting those backup scripts into a file, sequilaworldbackup.sql. To restore a database, we use the MySQL command line, logging in as root with a password, naming the database that we want to restore, and then passing in the backup SQL file for that database. And with this, the MySQL command line tool will reconstitute the Sequila database based on the contents of the Sequila backup.sql file. A database is ever changing. As data is inserted or deleted or updated within the database tables, the performance of the database will be impacted. As DBAs, we need to monitor this performance in order to ensure that the database is always operating optimally. The 4 resources on the server that the database is dependent on are the CPU, the disk storage, memory, and the network. In order to maintain the optimal performance of the database system, we need to have a starting point, a baseline measure of the performance of the server. This provides us many benefits. One, obviously, it gives us a starting point for optimization efforts. So if we know how the database performed yesterday, we can make a quantitative assessment of how it is performing today. Better, worse, the same. The other benefit of a baseline is that it documents the configuration of the server and provides us with the information we need to do capacity planning. So as we perform these monitoring functions of the database server, we can project future needs for disk space or expanding the memory or more CPU. So the starting point of any performance optimization effort is to have a performance baseline of the server. Once we've collected the baseline data, then we want to have a routine, a set schedule for collecting the same performance statistics that are contained in the baseline for comparison. One approach for doing this is to create a small administrative database on the server into which these performance statistics can be inserted, and we can then use that information to optimize the performance of the server. One of the realities of life as a DBA is that we will spend most of our time focused on a very small number of problematic queries, that is, queries that are causing performance issues on the server. And having that baseline helps us to identify those problematic queries to allow us to focus our efforts on those high frequency, poor performing queries rather than in other less productive areas trying to optimize the server. So let's go look at some code. In this demonstration, we're going to examine performance monitoring of the MySQL instance, with the understanding that there are many open source and fee-based tools for monitoring a MySQL instance. In fact, the MySQL community provides a tool called Enterprise Monitor that will monitor the performance of one or more MySQL instances. Unfortunately, that tool only runs within the Windows environment. However, there are many other tools. InnoTop is a clone of Top, which provides significant performance metrics for a MySQL instance. Percona offers a set of tools for monitoring a MySQL instance, and many others. And so you're encouraged to perform an internet search and examine these tools and find one you're comfortable with. Our focus is going to be on the native tools for performance monitoring, and one of those is the Server Status tab in Workbench. In this window, we can see the current status of our MySQL instance, from the load on the server, the number of connections on the server, the network traffic, the efficiency of the key lookups, how many queries per second are executing against the server, how much memory is currently being used by the server. Now, this is a measure of the percentage of the assigned memory that's being used, the number of reads and writes per second executed by the server. These are the basic metrics or performance measures that we need to monitor our MySQL instance. Another method for monitoring the instance is the show command. Internally, the MySQL instance maintains a set of performance variables, and we can use the show command to get the values that are being stored in those variables. The show command also allows us to query the status of the storage engine. Show engine, in this case InnoDB status, will return to us the internal performance metrics of the storage engine. There are a large number of internal performance variables that are maintained by the MySQL environment. This is a small representation of those variables. Using these variables, we can monitor the disk performance, we can monitor the memory performance, we can monitor the disk and key performance. We can even monitor slow running queries. Each of these variables provides an indication for us. That indication tells us where to go look for problems. So a slow running query would motivate us to go look at the slow query log. If we're having disk issues, then we want to go look at indexing and maybe the disk subsystem performance. And if we're having memory issues, then we need to examine whether or not the MySQL instance has enough assigned memory. And if the server itself has enough memory so that we might expand the assigned memory to the MySQL instance. Then at the operating system level, and again, remember, we're not trying to be Linux administrators, but as DBAs, we must also be comfortable with querying the operating system to examine the performance of the MySQL instance. And so we have several tools at the operating system level. One, obviously, is TOP, which reports the memory utilization, CPU utilization, and other statistics for all of the running processes in the system. And you'll see that our MySQL instance is listed here, and we can monitor its resource utilization using the top command. Also, we can monitor the memory status with vmstat, and each of these operating system commands have options that can be used to make them even more focused on the MySQL instance. IOStat provides performance metrics on the input and output to the disk and the performance of the disk subsystem. And the MPStat command provides information about CPU utilization. Each of these commands have options that can help us focus on the MySQL instance. Our goal is to monitor the performance of the MySQL system by monitoring the 4 key resources utilized by that system: CPU, memory, network, and the disk subsystems. In summary, as database administrators, our responsibilities are to the security of the database, the performance of the database, and the safety of the data contained within the database. These 3 responsibilities are equally important in our roles as DBAs. Remember that the driving principle of security of the database is the principle of least privilege. Give a user the permissions that user needs to perform the task that they are responsible for performing and nothing more. Create a baseline and regularly monitor the performance of the server, and develop a backup strategy. And not only develop the strategy and execute that strategy, but test the strategy. Because in many cases, an airtight database backup strategy has failed because it was never tested. So not only are we testing that the backup system is functioning, that the files are being created correctly, the scripts are being created correctly, but we're also testing our ability to reconstitute the database in the face of a system failure and the stress that comes with that scenario. When we're designing a database, our considerations are for the reduction of repetitive data, redundant data in the tables, and the elimination of data dependencies within a table. The result of that exercise is that we spread data across tables in the database. This works very well in supporting optimized storage utilization for the database. However, on the other side of the database equation, where we need to support data search and retrieval, we now have to spread that search and retrieval over multiple tables. To support the efficient search and retrieval of data, we need to implement database structures that assist the query optimizer and the data engine in finding the data that we request. Those mechanisms that assist in the search and retrieval of the data are referred to as indexes. As we've discussed, the InnoDB storage engine supports transactional processing systems. It does this by providing both implicit transactional support and explicit transactional control statements that we can use to manage our transactions. InnoDB also provides row-level locking in contrast to the MyISAM storage engine, which is generally used for data warehousing systems that support mostly read operations. Therefore, there is no transactional support provided, and all of the locking is done at the table level. Our focus in this discussion is going to be on the InnoDB storage engine and how we might design indexes for our data within that environment. An index on a database can be thought of much like an index in a book. If we want to find the page in a book where a specific keyword appears, we look in the index, and the index has a list of the pages within the book where that keyword appears. The characteristics of a book index are also shared by a database index. The database index requires extra space for storage. If we create an index that references other data in the database, then that index needs to be stored in the database and therefore requires more space. Likewise, as the data within the database is updated, deleted, or inserted, the index requires maintenance for the addition or the changes in the data. There are two types of indexes: the clustered index and an unclustered or non-clustered index. A clustered index is created when we define a primary key on a table. This is sometimes also referred to as the primary index. When we define the primary key, that causes the data within the table to be sorted and organized based on the value of the primary key. So a clustered index is actually the organization of the data itself within the table. In contrast, an unclustered or non-clustered index is a completely separate data structure from the table. When we define a non-clustered index, we are creating a separate data structure with the keys that we've chosen for the index organized and sorted, along with references to the location in the data table where the rest of the data for that row exists. So the key difference between a clustered and a non-clustered index is that a clustered index organizes the table based on the value of the primary key data. There is no other data structure created, while a non-clustered index is a separate, distinct data structure storing the keys of the index with references back to the table for the data associated with those keys. So recall when we were discussing primary keys during our table design discussion that when a primary key is defined, a clustered index is automatically defined on that table, and the clustered index organizes the data based on the primary key. So there can only be one clustered index. An important note is that the primary key size has an impact on the performance of the database. So we need to consider this when we're selecting the primary key to ensure that we're not selecting a primary key that will negatively impact the performance of the table. In general, because the data is organized in the order of the value of the primary key, searches on the primary key can be very, very fast. Again, this is dependent on careful consideration of which values use in defining the primary key. A non-clustered index, also referred to as an unclustered or secondary index, contains a subset of the data from the table. So we select some column from the table and we say, this column is going to be an index for the table, a value upon which we will search to find the rows of interest in the table. Now, the non-clustered index can consist of more than one column, but remember that the non-clustered index is a separate data structure. It requires disk space. And as we said, the non-clustered index carries with it a reference to the row in the data table corresponding to each key value in the index. This reference consists of the row ID, or the RID, of the data row in the data table to which the key corresponds. Now, one of the many drawbacks of non-clustered or secondary indexes is that whenever the data table changes, the index must also be updated. So an index is amazingly useful for a selection operation, but causes performance degradation for the other SQL operations, insert, update, and delete, because those operations require that the non-clustered index be updated along with the data table. There are some experiments that show that for an in-memory database, the insert, update, delete operations are about 2 times slower when using a secondary or non-clustered index. On the disk, this increases to 4 times slower. All indexes are stored as B+ tree data structures. We're not going to spend a lot of time talking about database theory or data structures and the theory behind what makes a B tree or a B+ tree the favored data structure for implementation of indexes and table structures within a database. That's not what this course is about, but it is important to know that the data structure behind the index is a B+ tree. So when we search for a value within a table, if we're searching based on a column, say column A, and our select statement contains a where clause that limits the return values to some range of values within those contained in column A, then the search key is that condition defined within the where clause and the column that is associated with that condition. So in this example, we have 2 columns, A and B, that are part of the search key. And we know that our queries in our application search on these 2 columns predominantly. We want to support those queries with an index to make their search faster. So we create an index, a separate data structure with just the columns A and B and the row ID back to the data table so that the select statement can also retrieve the values of the other columns, C, D, and E, if required. Now, we will look at another form of index referred to as a covering index, where extra data is carried along with the index key values. This extra data has no bearing whatsoever on the structure of the index. It's just baggage that's carried with the index key values so that the query engine does not have to go back to the data table using the row ID to retrieve data of interest to the query. But for now, we're going to focus simply on an index that supports a set of search keys based on the queries that are executed with the highest frequency in the application. That's our goal. This description is a little more theoretical in that it describes how a key value is translated from the index into the lookup for the data in the data table. And this is all based on the record ID or the row ID or the RID, however you'd like to refer to that piece of data that's carried with the index key value that refers back to the data table row associated with that key value. So the big question for a DBA in trying to optimize the performance of the database is, what indexes should I create? Why don't I just create indexes on all of the columns? Or why don't I just create very large indexes across multiple columns and let the query optimizer figure it out? Well, there's a lot of issues here to consider. One, storage space, because each non-clustered index requires extra storage space. This can be expensive. In addition, all of the other SQL commands, update, insert, and delete, are impacted by the existing non-clustered indexes. So the more indexes you have defined on a table, the slower the insert, update, or delete operations will be on that table. And in the real world, having multiple indexes on a table does not translate into exponential increases in the performance of the select statements. What we find is that a single well-designed index supporting a query will provide significant performance improvements for the select statement. So the questions we ask when we create an index are, what fields should I include in the index? Which queries need index support? And we're going to look at each of these questions and how best to design an indexing strategy for the table to make the selection fast while minimizing the impact on the other SQL operations. Optimizing the performance of a database begins with understanding how the database is being used by the application that it supports. Our goal is to identify that small number of queries that execute against the database with high frequency. Every application has a small number of queries that will execute against the database tens of thousands of times per day. These are the queries that are our focus for optimization. And when we create an index, it's important to test whether or not the index has actually impacted the performance of the query and not negatively impacted the performance of other queries executing against the database. Because remember that an index makes a select very, very fast, but negatively impacts the performance of updates, inserts, and deletes. Also, if our server is limited in disk space, then we must be very selective in creating secondary or non-clustered indexes, as these require disk space. They are separate data structures within the database. So how do we identify in the query which columns to include as index keys? Well, let's assume that we've identified a high-frequency query and that query selects some number of columns from the table and uses a filter, the where clause. The where clause is what filters the data for the select statement. So that's our focus. And within that where clause, the query has an equality condition. If the column upon which the equality condition is applied is not already part of the clustered index, that is the primary key for the table, then that column would be a candidate for a non-clustered index. We have not yet discussed joins. However, join conditions are also candidates for indexing, as they speed the process of combining table data. Recall that a clustered index organizes the data within the table. So it acts on the table itself, organizing the data based on the index key value. In the case of a clustered index, the index key value is the primary key of the table, so that the table data will be organized based on the value of the primary keys. This is especially useful for range conditions within the where clause and equality conditions. If we have a query that has multiple conditions in the where clause, then we want to consider having all of the columns that are included in the where clause condition statements in a single index. But be careful, because the order of the columns within the index will determine whether or not the query optimizer will take advantage of that index. And we talked a little bit about covering indexes. A covering index is simply a non-clustered index that carries extra data around with each of the key values. This extra data plays no role in the organization of the index B plus tree. It's just extra data that's being carried around. So in the example query, select name from employees where the age is equal to some value and the salary is equal to some value. Our index keys would be the age and the salary columns, and the included or covering column would be the name column. The query optimizer uses this index to find the values as defined in the where clause. It also finds the value of name associated with each of those matching values and does not have to do an additional read to the data table based on the row ID or RID that is associated with those index keys. It doesn't have to do that because the name column data, although not part of the index key, is carried with the index key data and is available for the query optimizer without having to go back to the data table. A covering index provides a significant performance boost by reducing the number of reads. So let's go look at some code. In this demonstration, we're going to examine the impact of indexing on the database performance. And to do that, we've created a table in the Sequila database. And this table uses the data from the native table actor. However, because the native table actor only had about 200 rows in it, we needed a table that had a significant number of rows so that we could get some quantitatively interesting numbers from our examination. So we've created a table called actors, plural, and this is the definition of the tables. An auto increment field for the primary key named actor ID, and then a first name and a last name. Very simple table. And we populated that table with the contents of the actor table in order to get a table with about 2.2 million rows in it. This is a decent sized table, not large by any measure, but decent sized. To test our performance, let's first clear the memory. So we're going to use the keyword flush. And flush tables is going to remove all of the data from memory. Flush query cache is going to remove all of the execution plans and saved queries from the query optimizer's cache. So let's execute this. And now let's make sure we don't have an index on our table. We're going to drop index. The index, if we have one, will be called IDX actor last name. I think I've already deleted this, and I have. So now let's run our select statement. We're doing a select statement, and we're asking for the primary key value, actor ID, and the actor's first name, but only those actors whose last names are Berry, Berry. So let's execute this, and we can see that it took roughly 1.5 seconds for this query to execute. Now, how did the query execute? What is it that the database system did to execute this query? Well, we can ask to see the execution plan that was developed by the query optimizer and used for the retrieval of this data. To do that, we use the keyword explain. And the explain keyword followed by the query of interest will return to us the query execution plan used by the database. So let's execute this. And we can see that the table upon which we queried was the actors table, and that there were no keys used in execution of the query because there is no key relevant to the where clause, where last name equals Berry. So the execution plan had to scan all 2.2 million rows in the table to find those where the last name equals Berry. So that's an expensive operation, having to look at all 2.2 million rows to find those of interest to us. So let's see what impact putting an index on the last name would have on this query. So now we're going to create, what are we going to create? Well, we're going to create an index. The name of the index is IDX underscore actor underscore last underscore name. So this is an index on the actor's last name. And we're putting this index on the Sequila actors table, the plural table, on the last name column. So let's execute this, and it is executing. It's a lot of disk activity because creating this index, this is a non-clustered secondary index on the column last name, which means that a distinct data object was created. A B plus tree was created to store the keys associated with this index. So now let's run our query again. And this time our query ran a little over half a second. So 3 times faster than the previous execution without the index. Let's see what the query optimizer developed for an execution plan. And sure enough, we're again acting on the actors table, and the query optimizer found that potentially it could use the index actor last name. And in its analysis, it found that it was indeed going to use that index. And the result of using that index was that the execution plan only had to touch about 64,000 rows versus the 2.2 million rows that had to be scanned in the previous execution. So this is a dramatic example of the impact of a simple index. So let's take this a step further now, and let's drop the index on the actor last name and now create a new index, a different index, because we've analyzed this query because we've decided to save a read back to the data table to retrieve the actor ID and first name we're going to include that data in the index so that when we find the last name of interest, the other data that the query requires will already be in the index structure. So we're going to save I/O by doing this. However, we're also going to increase the size of the index. So it's a trade-off, space for speed. So let's see how much faster now our query is going to be. So we've created this index, which is referred to as a covering index because it covers all of the required data of this query. The first name, the actor ID based on the last name value. Everything that the query optimizer needs to respond to the query is in the index structure. So now this execution is down to 6/100ths of a second from half a second previously when the index only contained the last name data. So let's confirm using the explain keyword that the query optimizer did in fact use this new covering index. And it did. Another dramatic example of the impact of efficient indexing on the selection of data from a table. Remember that when you're designing an index, the key values that you're looking for in the definition of the index are those values in the condition statements in the where clause. If we had a join where we bring two tables together, then the join condition columns would also be candidates for indexing. And had we identified this select statement as one of our high frequency queries, then this would be a good candidate for a covering index where we've decided to trade space on the disk for faster execution of the query. So in summary, when we're analyzing the database for the creation of indexes to support specific queries, we're looking to optimize the high frequency queries, those queries that execute thousands and perhaps tens of thousands of times per day against the database. This is where the largest performance improvement will be obtained. Remember that we don't want to just create indexes that don't have any benefit for a select query, because every index we create will slow all of the other table operations. The other consideration when creating indexes is the required disk space. Every non-clustered index will create a distinct data structure within the database, and that data structure will take resources, disk space. So the index can both be a great benefit to performance, increasing the performance of these high frequency queries, thereby increasing our database performance, and indirectly then increasing the application performance, providing our users with a positive experience. But there are downsides to be considered, that the other operations on the database will be impacted negatively, and that we need to manage our disk resources and not create indexes that, one, will not be used and therefore don't produce positive results for the database, and two, don't waste disk resources. The MySQL database system is a complex piece of software comprised of many different components that work together to provide the database services for our application. All of these components working together need to be configured optimally based on the available resources on the server. Often, new hardware is considered to improve the performance of a database system, when in fact a review and optimization of the database system's configuration settings would provide significant performance improvements. Recall that the database system is dependent on 4 system resources: the CPU, the disk, the network, and the memory. And our configuration settings can be tuned based on the availability of each of these resources on the hardware. Simply because we've tuned the configuration today doesn't mean that we can forget about it. A month from now, we should review the configuration and ensure that it remains optimal for the way the database is being used by the application, as well as any changes in the hardware. But as much tuning as we can do to the database system, we're still just one piece in the application stack. There's the web server to tune. There's the networking infrastructure to tune. Then there's the application code, where as a DBA, we know most of the performance problems exist. For the database server, these are the general recommendations for the configuration settings that affect the memory and the log and the concurrency within the server. In general, the database system will run on a dedicated server. So if that server has 32 gigabytes of memory, then the majority of that memory should be assigned to the database system. When we're using the binary log to support the durability of the database system, then writing to that log introduces performance issues. In version 5.6 of MySQL, the default size of the binary log is 50 megabytes. We may want to increase that if, when we're monitoring the server, we see issues with writing to the log and log flushes, then we may want to increase the size of the log. However, in increasing the size of the log, if we suffer a system failure, the larger the binary log, the longer the recovery time. And there are other optimizations that, depending on our application and the hardware upon which the database server is running, we may want to make. So let's go look at some code. In this demonstration, we're going to examine the MySQL database configuration settings, and we're going to look at them with the goal of optimizing the performance of the server. There is no magic number for these settings. They are dependent on the application characteristics. We can look at the configuration settings by using the show command, or we can examine these settings by opening the Status and System Variables tab in the Workbench and going to System Variables. In this view, we have access to all of the configuration settings for the system. We're going to stick with the script version. So we're going to show global variables. And which one do we want to look at? The first one we're going to look at is the flush log at transaction commit value. And when we run this, we see that the configuration setting is at 1, which is the default and is the only setting which is ACID compliant. The other 2 possible settings are 0 and 2. However, with either of those settings, we can lose data in the transaction log. About a second's worth of data, so it's not a lot of data, but we can lose data, and that violates ACID. So we're going to leave this at 1. If we see issues with the log file during the execution of our application, then we may want to increase the log file size. The default log file size is 50 megs. That can be small for most applications. This setting must be adjusted in the configuration file, the my.cnf configuration file. And when this setting is changed in that file, the MySQL service must be restarted. A good recommended setting for the log file size, again, very dependent on the application, is about 256 megs. Remember that the larger the log file, the longer the recovery time in case of a system failure. How about thread concurrency? Well, thread concurrency in the InnoDB engine by default is set to 0. This is a setting that should be adjusted based on the number of available CPUs. The configuration setting for the buffer pool size, that is the data memory that the engine uses, is also adjusted in the configuration file, and when adjusted, the server must be restarted. This configuration setting should be maximized to 80 or 90% of the available memory on the system for the best performance. The number of pool instances, the number of data memory pool instances, is also adjusted in the configuration file. Having a higher number for this configuration setting will reduce contention in the buffer pool. We've provided a sample my.cnf file for the configuration of a OLTP MySQL installation. Like any sample my.cnf configuration file, this file should not be taken at face value. Review the settings, test it against your application, and ensure that the system operates optimally. All of the configuration settings for the system may be defined within the configuration file. Be careful which my.cnf file is modified to ensure that it is the file that is being read during the service startup. In summary, there is no magic number for any of the configuration settings for the MySQL database system. The best setting may only be determined through experimentation. Set the value, measure the performance over time, and adjust as necessary.
If you're not a subscriber, click down below to subscribe so you get notified about similar videos we upload. To see the full course that this video came from, click over there. And click over there to see more videos from Simon Sez IT.